Welcome to Grandpa's Late Nights. Come on in, pull the blanket up over your shoulders the way you like it, right up under your chin. Let your head sink into the pillow. There's no hurry tonight. There's nowhere either of us has to be. The porch light's on outside, the way it always is, and the house is quiet, and the only thing on your list of things to do is to lie there and breathe slow and let your old grandpa tell you a story about the sky. So let me start with a number. Just one small number. Kiddo. Not a big scary equation, not a chalkboard full of symbols. Just one number, and it's the kind of number you could write on the back of your hand. That number is -1. -1. That's it. And I want you to hold on to it gently, the way you'd hold a smooth stone you picked up at the beach, because for 25 years, a full quarter of a century, longer than some of the people reading the news about this, have been alive. The smartest people on Earth were absolutely certain that this one number, this -1, was fixed, locked, set in stone, never moving, never wobbling, never changing, not yesterday, not today, not a billion years from now. And then, just a little while ago, the universe handed us a new map. The biggest map of the sky anyone has ever made. And that map leaned over and whispered something that made a lot of very serious, very careful people go very quiet all at once. It whispered that maybe, just maybe, that number isn't -1 after all. And if it isn't, kiddo, then something we thought we understood about the whole entire universe, about how everything ends, was wrong. But don't you worry about any of that just yet. We've got all night. Let me back up and tell it slow, the way these things ought to be told, with the lamp low and the clock ticking soft in the hall. Here's the thing you have to understand first. When you look up at the night sky, really look, on a clear, cold night far from the town lights, it seems so still, so permanent. Those stars look like they've been pinned up there forever and always will be. The whole sky feels like something you could set your watch by. Fixed, reliable, the one thing in life that never changes. But it's not still at all. The whole universe is stretching, growing. Every single moment, the space between the galaxies is getting bigger. Not because the galaxies are flying apart through space like pieces of a firework. No, it's stranger and gentler than that. It's the space itself, the empty room between everything, that's swelling up, getting roomier. Think of it like this. Imagine you've got a loaf of raisin bread rising slowly in a warm kitchen. The raisins aren't crawling through the dough. They're just sitting still, minding their own business. But as the dough rises all around them, every raisin drifts away from every other raisin, because there's more and more bread being made in all the gaps between them. That's the universe. The galaxies are the raisins. And the dough, the empty space, keeps rising and rising and rising. Now, for a long time, people figured that this stretching ought to be slowing down. And that made a good deal of sense if you think about it. Everything in the universe pulls on everything else with gravity. Every galaxy tugs on every other galaxy, ever so faintly, across the dark. So you'd expect all that pulling to act like a brake. Like a ball you toss up in the air, it goes up fast, then slower still, and eventually gravity wins, and it comes back down to your hand. The expectation was that the whole cosmos was like that thrown ball, flung outward long ago in the beginning, and gradually, patiently, being reeled back in by the gentle break of gravity. Slowing down, maybe someday stopping, maybe someday falling back together. That was the sensible bet. That was what nearly everyone expected. And then, back in 1998, and I want you to remember that year because it's the year the story really turns, two teams of astronomers set out to measure exactly how much the universe was slowing down. Let me tell you about these two teams, because they weren't working together, kiddo. They were rivals, racing each other. Two separate groups of very stubborn, very clever people, each one trying to be the first to pin down the number. One team was called the Supernova Cosmology Project, led by a fellow named Saul Perlmutter, and the other was called the High Z Supernova Search Team, and that one was led by two men, Brian Schmidt and Adam Rees. And both teams were hunting the same kind of quarry across the night sky. They were hunting exploding stars. Now let me tell you what kind of exploding star, because this is one of those beautiful little tricks of nature that makes the whole thing possible. And I don't want you to miss it. There's a particular kind of stellar explosion called a Type 1a supernova. Say it slow with me if you like, a Type 1a supernova. And the wonderful thing about this kind of explosion, the thing that makes it so useful, is that they all go off with almost exactly the same brightness. Every single one. It's as if the universe manufactured a whole warehouse of identical light bulbs and scattered them across the cosmos, and every bulb, when it flares up, shines with the very same wattage as all the others. Now, why does that matter? Think about it this way. Imagine you're standing on your porch at night, and way off down the road you can see a street lamp. And suppose I told you every street lamp in the whole country was built to shine with exactly the same brightness. Well then, just by seeing how dim or how bright a particular lamp looked to your eye, you could tell how far away it was. A lamp that looks nice and bright must be close. A lamp that looks faint and small must be far, far down the road. You wouldn't have to walk out and measure it with a tape. The dimness itself tells you the distance. Astronomers call these things standard candles, and that's a lovely name for them, isn't it? A candle whose true flame you already know, so its faintness becomes a ruler. So these two rival teams went out hunting these standard candles, these Type 1a supernovae, far, far away across the universe. And by measuring how faint each one looked, they could figure out how far away it was. And here's the other clever piece. Because light takes so long to cross the universe, when you look at something very far away, you're not seeing it as it is now. You're seeing it as it was long ago, when that light first set out on its journey toward you. So these faraway exploding stars were like little time-stamped postcards, telling both how far and how long ago. And both teams expected the same thing. They expected to find that the faraway supernovae, the old ones, the ancient ones, would show a universe that used to expand faster than it does now. Because remember, everyone thought gravity was the brake. Everyone thought the expansion had been slowing down over the ages, so the deep past should look speedy and the present should look slower. But that's not what they found. Both teams, working separately, racing each other, got the same impossible answer. The distant supernovae were too faint, fainter than they should have been, farther away than they had any right to be. And when the astronomers worked backward from that, when they followed the arithmetic to where it led, they arrived at a conclusion so strange that at first several of them thought they'd made a mistake somewhere. They checked it and checked it again. The universe wasn't slowing down, the universe was speeding up. The stretching was getting faster, the expansion was accelerating. Now sit with how peculiar that is, kiddo, because I don't want it to slide past you in the dark. It's as if you tossed that ball up into the air, and instead of slowing, stopping, and falling back to your hand, it slowed for just a moment, and then, all on its own, with no hand pushing it, no engine, no rocket. It started to rise faster and faster, climbing away from you into the sky, gaining speed as it went, until it vanished. That's not supposed to happen. Balls don't do that. Nothing you've ever thrown does that. There has to be something pushing. Some force, some pressure, some hidden hand in the empty dark, shoving everything apart harder and harder as the eons roll by. Nobody knew what that something was. Nobody knows entirely, even now. But they had to call it something, so they gave it a name. They called it Dark Energy. And I'll be honest with you, that name is really just a polite way of saying we don't know. It's not dark like a shadow. It doesn't have anything to do with the dark matter you might have heard of. And I want you to keep those two separate in your sleepy head, because folks mix them up all the time and they are not the same thing at all. Dark energy is this pushing, this stretching pressure woven into the emptiness itself. That's all the name means. The force pulling the universe apart. The mystery in the empty room. That discovery, that accelerating universe, was so profound and so unexpected that 13 years later, in 2011, those three men, Saul Perlmutter, Brian Schmidt, and Adam Riess, were awarded the Nobel Prize in Physics for it. The highest honor there is, given for finding a thing nobody wanted to be true, a thing nobody had ordered, a thing that just turned out to be so. And here's a fact to lull you into the proper sense of scale. This dark energy, this whatever it is doing all the pushing, it isn't some minor ingredient, some pinch of salt in the recipe of the cosmos. It's most of the cosmos. If you take everything in the entire universe, every star, every planet, every galaxy, every cloud of gas, every scrap of matter, and every whisper of energy, and you add it all up into 100%, then dark energy is about 68% of it. 68%, kiddo. More than 2/3 of all that exists is this stuff we can't see, can't bottle, can't fully explain. Another 27% or so is dark matter. That's a different mystery for a different night. And everything else, all the ordinary stuff, all the atoms, every star you've ever wished on, the ground under your house, the very bones in your hand, you, me, the whole solid furniture of the world, all of that is only about 5%. Let that settle over you like a second blanket. The universe is dominated, ruled really, by the one thing we understand the least. The great ocean is dark energy, and everything we know and love is just a little foam on top of the waves. So there we were. We'd found this dark energy back in 1998. We knew it was pushing everything apart, faster and faster. We knew it made up most of everything. And there was one big question left hanging in the air, the question that everything else would come to depend on. And that question was this: is dark energy staying the same? Or is it changing? And here, my dear one, is where I have to introduce you, very gently, to that little number I mentioned at the very start. The negative one. Because that number is how the scientists keep track of the answer to that very question. You don't need to do any math, I promise. Just picture the number as a kind of dial. A single dial on the great dashboard of the universe, and that dial measures the character of dark energy, how it behaves, whether it holds steady or drifts. The scientists have a name for that dial. They call it W, just the letter W. And for the simplest, tidiest, most beautiful version of the whole story, that dial sits at exactly -1. -1. And this is the important part, so let it sink in slow. If the dial is truly exactly at -1, then dark energy never changes. Not ever. It was the same strength when the first stars were born as it is right now, as it will be 100 billion years from tonight. Steady, constant, woven into the fabric of empty space itself and utterly unchanging. That idea that dark energy is constant has a proper name too, and it's an old one. Older than the discovery of 1998. It goes all the way back to a man you've surely heard of, Albert Einstein. Way back in 1917, long before anybody had the faintest notion of dark energy or accelerating universes, Einstein was working out his great theory of gravity. And he found he needed to add a little something to his equations to make them behave, a little extra term, a constant. And he wrote it with a Greek letter. The letter lambda, it looks like a little tent, or an upside-down Y, or a pair of legs walking. Lambda, and Einstein's lambda was, in its heart, exactly this idea, a fixed, constant energy sewn into the emptiness of space. The same everywhere and always. So when scientists put together their best, most complete picture of the whole universe, how it began, how it grew, how it's shaped, where it's going, they built it around this constant lambda. That's why the standard model of the cosmos, the reigning picture that's been on the throne for decades, carries lambda's name right in its title. They call it Lambda-CDM, Lambda-CDM. And that lambda, right there at the front of the name, is the assumption that dark energy is constant, that the dial sits forever at -1. Now here's what I want you to really understand tonight, the thing that took me a while to appreciate myself. For all these years, when people talked about dark energy, they'd shake their heads and say, "Oh, it's such a mystery. We don't know what it is." And that's true. We don't. But that mystery was never really the load-bearing beam of the whole structure. Not knowing what dark energy is made of, that we could live with, that we'd made our peace with. The thing everyone was actually leaning on, the assumption holding up the roof, wasn't we know what dark energy is. It was whatever dark energy is, at least we know it's constant. At least the dial's at -1 and it stays there. Because that one assumption, the constancy, is what let us do something remarkable. It's what let us predict the end of the universe, the whole ending. If dark energy is constant, then the story of how everything finishes is more or less settled. The universe keeps stretching, faster and faster, forever and ever. The galaxies drifting apart into the cold and the dark until the lights all wink out one by one. A quiet, frozen, endless ending. We'll get into all that on another night. The point for now is just this. That whole grand prophecy about the fate of everything rests squarely on the assumption that the dial doesn't move. That equals -1. Now and always. Take away the constancy, and you don't just lose a footnote. You lose the ending. You lose the ability to say how the story finishes at all. And that, kiddo, is exactly what started to happen. Because here's the trouble with an assumption. You can lean on it for 25 years, so long and so hard that you almost forget it's an assumption at all. It stops feeling like a guess and starts feeling like a fact, like the floor under your feet. Nobody had ever actually watched dark energy over time to check whether it holds steady. How could they? You can't set up a stopwatch and wait 1 billion years. You can't run the universe in a laboratory. For a quarter of a century, the constancy of dark energy wasn't something we'd confirmed. It was something we'd assumed because it was simple, because it was beautiful, because Einstein's tidy little constant fit the equations so nicely, and because we had no evidence pushing us to think otherwise. Simple and beautiful and unchecked. That's a dangerous combination in this world, and the sky was about to prove it. So the real question, the one that would take a machine that hadn't even been built yet, was whether anyone could find a way to actually watch. Not assume, not hope, not lean on Einstein's elegant guess, but genuinely look back across the enormous gulf of cosmic time and measure that dial, that W, at different moments in the universe's long life. Measure it when the universe was young. Measure it in middle age. Measure it now. And lay those measurements side by side and simply see, did the number stay put at -1? Or did it drift? Because if you could do that, if you could line up dark energy strength across billions of years like beads on a string, then you'd finally know. Not guess. Know whether the one thing we were sure of was true. And a few years back, they built the machine that could do exactly that. And they pointed it at the sky, and they made the largest map of the universe that human beings have ever made, millions upon millions of galaxies, stretched across 11 billion years of cosmic history. And when they read that map, when they finally got to watch dark energy change through time instead of just assuming it never did, what it showed them was the one thing the standard model says can't happen. The dial wasn't sitting still at -1. It looked like it had moved. It looked like dark energy had been stronger long ago, back in the deep and ancient past, and that it's been quietly, steadily weakening ever since, easing its grip, growing tired, right up to this very night. And a cosmological constant, a true, honest, Einstein-style constant, is mathematically forbidden from doing that. It's not allowed. It cannot move. That's the whole point of it. So if the map is right, then it isn't a constant at all. And if it isn't a constant, then the load-bearing beam, the one everyone's been leaning on for 25 years, the assumption that quietly holds up the entire predicted future of the universe, that beam just made a sound. A small, dry, cracking sound, way up in the rafters in the middle of the night. Now I can feel you getting curious, and that's good. That's just how a story ought to make you feel. You want to know how in the world anybody could possibly measure such a thing, how you could take a machine sitting on a mountain in the desert and use it to watch a mysterious force fade across 11 billion years. It sounds like magic. It sounds impossible. And I promise you, before this night is through, I'll walk you through exactly how they pulled it off, slow and clear, one piece at a time, and it's one of the most beautiful tricks in all of science. It involves a frozen sound wave, if you can believe that, a ripple stamped into the sky so long ago that it's now nearly 500 million light-years across. But not yet. For now, just rest with the shape of it. Just hold the wonder of it in your hands like that smooth beach stone. For 25 years, we were sure of exactly one thing about the most powerful, most abundant stuff in all the universe. Not what it was. We never knew that. But that it never changed. That its number was fixed at -1, steady as the North Star, dependable as sunrise. We built our whole picture of the beginning and the end of everything on top of that one steady number. And now the newest, biggest, most careful map ever made has looked back across almost the entire life of the cosmos, and it's murmuring that the number might be moving. That the force pulling the universe apart may be getting weaker. That the one thing we were sure of about the thing we understand the least may, after all this time, turn out to be wrong. The people who found this aren't shouting it from the rooftops. Kiddo, that's the other part of the story, and it's a part I've grown to love. They're not celebrating. They're being careful, almost painfully careful, because they know what's at stake. And they know how many times the sky has fooled clever people before. There's a line these measurements have to cross before anyone's allowed to say the word discovery out loud, and this one hasn't quite crossed it. It's close. Close enough to keep a cosmologist awake at night, staring at the ceiling. But not quite close enough to say for certain. And that space, that thin, trembling gap between it looks like everything we thought is wrong, but we're not allowed to say so yet. That's where the whole field is sitting right now. Holding its breath. Waiting. So settle in a little deeper. And let your eyes go soft. And let me tell you how they built the machine that watches the past. Let me start at the beginning of it all, back in 1917, when a man named Albert Einstein was staring at his own equations and feeling something close to worry. His new theory of gravity was beautiful. It described how matter bends space, how the whole grand scaffolding of the cosmos hangs together. But it had a stubborn habit he didn't like. Left to itself, the universe in his equations wanted to move. It wanted to collapse inward under its own weight, all that matter pulling on all that other matter, drawing everything toward a single point. That bothered him, because in those days, everyone was sure the universe just sat there. Fixed, eternal, a still room with the stars nailed to the walls. So Einstein did something that would haunt and vindicate him by turns for the rest of his life. He reached into his equations and added one more term. A little counterweight, a gentle outward push woven into the fabric of empty space itself, just strong enough to hold the collapse at bay and keep the room still. He called it the cosmological constant, and he marked it with the Greek letter lambda. That little. Remember that letter, kiddo, because it's going to sit at the center of everything I tell you tonight. Now here's the thing about that push. It wasn't a thing floating in space. It was a property of space, of nothing at all. The idea was that even perfectly empty space, no stars, no dust, no light, just pure void, even that has a faint energy to it, and that energy pushes outward, and because it belongs to the emptiness itself, it never runs out. Stretch the universe bigger, make more empty space, and you've simply made more of the push. It grows as the room grows. It can't dilute, it can't fade. That was the whole point of it. Constant, fixed, the same, yesterday, today, and forever. For a while, Einstein came to regret the whole business, when other astronomers showed that the universe wasn't sitting still at all, that it was flying apart, galaxies rushing away from one another in every direction. He felt he'd added his little counterweight for nothing. The story goes that he called it his greatest blunder, though whether he ever really said those exact words is a bit of a campfire legend now, passed hand to hand, until nobody's quite sure of the source. Either way, he set the idea down and walked away from it, thinking the cosmos had no need of a lambda after all. He had no way of knowing he'd been right for the wrong reasons. That his throwaway term would come clawing back 3/4 of a century later, wearing a new name and carrying a mystery big enough to swallow the whole field. That reckoning came in 1998, and it came the way the best discoveries so often do, by accident, from people looking for something else entirely. 2 teams were out hunting in the dark that year, and they weren't even friendly about it. Rivals, racing each other. One called itself the Supernova Cosmology Project, led by a man named Saul Perlmutter. The other went by the High Z Supernova Search Team, and its leading figures were Brian Schmidt and a younger fellow named Adam Ries. Both teams were chasing the same quarry across the sky, a particular kind of exploding star. Let me tell you about those stars, because they're the closest thing astronomy has to a perfect measuring tool. A Type 1 supernova. When a certain kind of dead star reaches a certain critical mass and detonates, it always goes off with very nearly the same true brightness. Every single time. That's the gift of it. If you know how bright a thing truly is, and you can see how bright it merely looks from here, then the dimness tells you exactly how far away it is. A candle held close is blinding. The same candle a mile off is a pinprick. Astronomers call these stars standard candles, and they're strewn across the whole depth of the universe like lanterns hung down a well. So both teams went looking for these distant lanterns, measuring how dim they were, expecting to answer what everyone assumed was the real question. Everybody knew the universe was expanding. The only argument left, they thought, was about how much it was slowing down. Because gravity should be putting the brakes on, shouldn't it? All that matter tugging inward, trying to reel the galaxies back home. They expected to catch the expansion decelerating, easing off the gas, and they only disagreed on by how much. That is not what they found. The distant supernovae came back dimmer than they had any right to be. Dimmer means farther. Farther than a slowing universe could possibly have carried them in the time available. There was only one way to read it, and it made no sense at all. The expansion wasn't slowing down, it was speeding up. Something was pressing down on the accelerator. Something was pushing the whole universe apart, harder and harder as time went on. Both teams saw the same impossible thing from opposite sides of their rivalry, and that agreement is what made the world believe it. It's one thing when your friends confirm your result. It's another thing entirely when your competitors, working to prove you wrong, stumble into the exact same answer. The whole field had to sit down. The number Einstein had penciled in and erased was suddenly the only thing that could explain the sky. They gave that mysterious outward push a new name, dark energy, and years later, in 2011, they handed Perlmutter, Schmidt, and Ries the Nobel Prize in Physics for finding it. And here's where the strangeness really starts to bite, kiddo. Because once they knew to look for it, they added up how much of it there had to be, how much of this dark energy the universe needed to be flying apart the way it is. And the answer stopped everybody cold. Dark energy makes up something like 68% of everything, more than 2/3 of the entire energy content of the cosmos. Then there's another mysterious ingredient. Dark matter, holding galaxies together. That's around 27%. And everything else, every star, every planet, every mountain and ocean and living thing, every atom you've ever seen or touched or been, all of that ordinary matter is barely 5% of the whole. Turn that over slowly. The universe is a house, and we live in one small lit room of it, and that room is 5% of the floor plan. The other 95% is dark on our maps, and the single biggest part of it, that dominant 68%, the thing that outweighs everything else combined, that is the part we understand the very least. We named it, and naming a thing feels like knowing it, but we didn't understand it. We still don't. Except we thought we knew one thing. Just one. We didn't know what dark energy was, but we were sure of how it behaved. We were sure it was constant, Einstein's fixed push, the same everywhere, unchanging across all of time, exactly as the cosmological constant demanded. That was the bedrock under the whole enterprise. Not we understand it. We never claimed that. The claim was quieter and far more important. The claim was, whatever this thing is, it doesn't change. And that, kiddo, that one load-bearing assumption, the beam holding up the entire ceiling, is the thing the new map just leaned on and felt it give. So let's talk about that beam. The cosmological constant. Lambda, that little Greek letter, that's sitting in Einstein's equations like a quiet, permanent guest who never leaves and never changes. To understand why DESI's results matter, to really feel the weight of what they're suggesting, you need to understand what the word constant actually means when a physicist uses it. Because it doesn't just mean unchanging in the way a rock is unchanging or a painting is unchanging. It means something deeper and stranger. It means woven into the fabric of what space is, inseparable from the geometry of emptiness, fixed not by circumstance but by fundamental law. A constant in this sense isn't something that happens to stay still, it's something that cannot move. Think of it this way. You have a room. The room has a certain amount of air in it. You push the walls out, the room gets bigger, and the air spreads to fill the new space. More volume, same air, so the density of the air per cubic foot drops. That's what happens to almost everything as the universe expands, matter thins out. As galaxies race apart and the cosmos grows, the stuff inside it gets more spread out, more diluted, more faint, like ink dropped into a growing glass of water. Dark energy, under the cosmological constant, does not do that. It refuses. As the universe expands and creates new space, the energy density of that new space is the same as the energy density of the old space. The new space isn't borrowing energy from somewhere else, and it isn't creating a deficit somewhere. The energy is native to the space itself, built into emptiness the way wetness is built into water. You can't have space without it, any more than you can have a shadow without a surface. Every cubic meter of vacuum carries a fixed amount of this energy. Make more cubic meters and you make more of the energy. Perfectly, proportionally, forever, same push per unit volume, always, everywhere, without variation. That's the constant. That's lambda. Not a thing that lives inside the universe. A property of the universe's structure, the way tension is a property of a spring. And because the energy density never drops, the outward push never weakens. More space means more total dark energy, which means more expansion, which means more space, which means more dark energy, a runaway that never runs out of fuel, because space itself is the fuel and space never runs out. This is what made the 1998 discovery so unsettling and so durable. Once the acceleration was confirmed, once Perlmutter and Schmidt and Riess and their collaborators stared at those dimmer-than-expected supernovae and understood what they were looking at, the cosmological constant was the most natural explanation. Because Einstein had written it into the field equations back in 1917, almost as an afterthought, a term he added to keep the universe static, which was what he thought it was at the time. He'd never meant it as a description of real physics. He introduced it, decided later it was a blunder, took it back, or tried to. But the equations kept it. The equations have a kind of stubbornness about them. And when the acceleration showed up in 1998, there was lambda, waiting, already in the equations, already the right shape, already fitting. Like finding a key in an old coat pocket that opens a door you didn't know you'd been locked out of. So Lambda-CDM became the standard model of cosmology. Lambda for the dark energy constant, CDM for cold dark matter, built on those two dark pillars and the familiar ordinary matter underneath them. It predicted cosmic expansion. It matched observation after observation. For 25 years it held. And underneath all of it was that single structural requirement, the equation of state parameter, W must equal exactly -1. Not -1.1, not -0.9. Exactly, precisely, permanently -1. That was worth staying with for a moment, because it's the number at the heart of everything that follows. What it measures is the relationship between the pressure dark energy exerts and its energy density. For normal matter, that ratio is close to 0. Matter has energy, but not much internal pressure in the cosmic sense. For radiation, it's positive. For a cosmological constant, W is -1. Negative, because dark energy doesn't pull inward the way gravity does. It has a repulsive quality, a negative pressure, a push rather than a pull. And it's exactly 1, not approximately 1, not 1 on average, because the pressure and energy density are perfectly immutably coupled. If the energy density doesn't change, neither does the pressure. -1, locked, for the entire age and future of the universe. Now, if V equals -1 and doesn't drift, you can calculate the future. The expansion rate now, the density now, the equations of general relativity. Put those together and they tell you where this is all going. The answer they've given for 25 years is something called the heat death, or the big freeze. All the same thing, different names for the same quiet ending. What it means, the expansion keeps accelerating. Over billions and billions of years, the galaxies beyond our local group, beyond our small gravitationally bound neighborhood of the Milky Way and Andromeda and a few dozen smaller companions, those galaxies accelerate away from us faster and faster until they're moving away faster than light. Not because they're traveling through space quickly, because space itself between us and them is growing fast enough that the light they emit never reaches us. They fall beyond the cosmological horizon. They vanish. One by one, and then in clusters, and then in superclusters, the universe goes dark to us, each island of light sliding behind a horizon we can never cross. The stars burn out. The last red dwarfs, the most frugal of them, burning hydrogen at a miserly pace, live for trillions of years, 10 trillion, 100 trillion, numbers so large they have no intuitive meaning, but they end too. Then the remnants cool, white dwarfs growing dimmer over eons, neutron stars going cold, black holes slowly, impossibly slowly, radiating away through Hawking radiation until they too dissolve into the last faint breath of particles. And then nothing. A vast dark cold expanding emptiness, growing colder and emptier as it expands, approaching, never quite reaching, the maximum entropy that is perfect, uniform, dead equilibrium. That's the forecast. 100 followed by 99 zeros of years from now, give or take. The universe not ending with a bang, but dissolving like sugar in an infinite, lightless sea. That forecast depends entirely on W staying at -1. If it doesn't stay there, if it moves, the forecast changes. Maybe a little, maybe completely. And the thing about forecasts is that we trust them precisely as much as we trust the assumptions they're built on. The moment an assumption wobbles, the forecast wobbles with it. So the question became, can we actually test whether W is exactly -1? Not assume it, not infer it from equations. Test it, measure dark energy's behavior across time, and see if it holds its value or drifts. That question needed an instrument, something that could look across billions of light years, gather light from millions of galaxies, and do so with enough precision to watch the expansion rate tick forward and backward through the deep past. Something that could take the temperature of the universe at different ages and compare the readings. The kind of machine that sounds, honestly, like something you'd read about in a science fiction novel and then remind yourself doesn't exist yet. It exists. It's called DESI, the Dark Energy Spectroscopic Instrument. It sits on a telescope in the Sonoran Desert in Arizona on a mountain called Kitt Peak at an altitude of about 2 kilometers. The telescope itself, the Nicholas U. Male telescope, is 4 meters across at the mirror, which doesn't sound enormous until you consider what that mirror gathers: light that in some cases left its source 8, 9, 10 billion years ago, before the Earth existed, before the Sun existed, from galaxies so remote that we have no intuitive sense of the distance. The light takes that long to get here. And when it does, it lands on this mirror in the desert and then travels into an instrument unlike almost anything built before. The instrument's core trick, the thing that makes it so powerful, is 5,000 robotic arms. 5,000 of them, each one tipped with a fiber optic cable, each cable thinner than a human hair, each arm able to pivot and reposition autonomously in about a minute. They sit in a circular focal plane, the plane where the telescope's optics bring the light to focus, and they are aimed, each one independently, at individual galaxies in the sky above. Not one at a time. 5,000 at once. Close your eyes and picture it, a night sky full of galaxies, thousands of them in the field of view of this one telescope, each one a dim smudge of light. And below the mirror, 5,000 tiny robotic fingers, each bend toward a specific smudge, each one picking up the light from one galaxy and routing it through its hair, thin cable, down to a spectrograph. 5,000 galaxies. Simultaneously, and after each exposure, after the light has been gathered and recorded, the robotic arms reconfigure, pivoting in seconds to new targets, a new field. 5,000 more galaxies, night after night. The spectrograph is what turns the light into information. It spreads each beam of gathered light into a spectrum, a rainbow essentially, the colors laid out in order from red to blue. And buried in that spectrum, like a fingerprint, is information about the galaxy's motion. Because atoms emit and absorb light at very specific wavelengths, very specific colors. Hydrogen, the most abundant element in the universe, has its signatures. So does oxygen, carbon, magnesium. Those signatures appear in every galaxy's spectrum as bright or dark lines at known positions. Except when the galaxy is moving away, those positions shift. The whole spectrum stretches toward the red end. The further away the galaxy, the faster it's receding due to expansion, and the more its spectrum shifts. This is called redshift. And the amount of redshift, the precise measurement of how much the spectral lines have moved from where they should be, tells you exactly how far away the galaxy is, and, because distance equals time when it comes to light, exactly how long ago its light was emitted. Here's where it becomes something more than a measuring tool. Here's where it becomes a time machine. When you point a telescope at a galaxy and measure its redshift, you're not just finding out where it is, you're finding out when it is. A galaxy with a redshift that says its light traveled for 2 billion years is showing you the universe as it was 2 billion years ago. A galaxy whose light traveled for 8 billion years is a window into the cosmos when it was barely half its current age. Look across a wide enough range of redshifts, gather enough galaxies from enough different distances, and therefore different eras, and you're not looking at a snapshot, you're watching a film. the universe evolving over billions of years, frame by frame, each frame a different distance, a different age, a different expansion rate. This is what DESI does on an almost incomprehensible scale. Its first major results, released in April 2024, were built on the spectra of roughly 6 million galaxies and quasars, quasars being the brilliantly luminous cores of distant galaxies powered by supermassive black holes, bright enough to be seen from nearly the beginning of the observable universe. 6 million objects, each one tagged in 3 dimensions, mapped to its position in space and its position in time. Together they form a 3-dimensional map that spans billions of light-years in every direction. Then DESI kept going. By March 2025, the second major data release, DR2, expanded the map to nearly 15 million galaxies and quasars, covering roughly 11 billion years of cosmic history. 11 billion years. The universe is thought to be about 13.8 billion years old, which means DESI's map reaches back to when the universe was barely 2.5 billion years old. Younger than the Earth is now. That map, as of early 2025, was the largest 3-dimensional survey of the cosmos ever made by human beings. The biggest map, the deepest reach, the widest window in time we've ever opened. And the point of all this, the reason to build such an instrument, to map so many galaxies over so many nights, is to find the ruler. Not a literal ruler, though the word ruler is exactly right in spirit. There's a pattern hidden in the distribution of galaxies, a scale, a characteristic separation, a preferred distance at which galaxies cluster slightly more than average. It's subtle, you wouldn't see it looking at any small patch of sky, but measure enough galaxies, map them accurately enough in 3 dimensions, and a statistical ripple emerges. Galaxies are, ever so slightly, more likely to be found at a specific distance from each other. A bump in the probability distribution. A gentle preference for a particular spacing. That spacing, that preferred separation, is about 490 million light-years. Call it, loosely, 500 million light-years, though the precision matters and we should keep it at 490. 490 million light-years stamped into the large-scale structure of the universe. Where did it come from? From sound. From actual sound, of a kind, though the analogy needs unpacking. In the first 380,000 years after the Big Bang, a cosmic instant. Compared to the 13.8 billion years since, the universe was a fireball, hot beyond imagining. Not empty space with stars in it, but a churning plasma, a fog of electrons and protons and photons so densely packed and energetic that light couldn't travel freely. It was absorbed and re-emitted almost immediately. The whole thing was opaque. And it was not still. It was turbulent, it had pressure. And in a medium with pressure, disturbances travel as waves, not light waves, which were trapped, but pressure waves, acoustic waves, sound waves, in the loosest physical sense of the word. These waves rippled outward through the plasma from any point of density perturbation, any place where matter was very slightly clumped due to quantum fluctuations at the universe's very beginning. They propagated at enormous speed, roughly half the speed of light, because the medium they traveled through was so hot and dense. And they expanded, like ripples from a stone dropped in water, moving outward for as long as the plasma existed. 380,000 years in, everything changed. The universe had been expanding and cooling since the beginning, and by that point it had cooled enough for something crucial to happen. Electrons, which had been free roaming in the plasma, slowed down enough to be captured by protons. They combined, Hydrogen atoms formed, neutral atoms, for the first time. And neutral atoms don't interact with photons the same way ions do. The fog cleared. Light was suddenly free to travel. The universe became transparent. When that happened, the pressure waves stopped. Not gradually, almost instantly, on cosmic timescales. The medium that supported them became electrically neutral. The coupling between matter and radiation collapsed, and the waves froze. Whatever shape they were in at that moment, that's the shape they locked into. They didn't die. They crystallized. Their leading edge, the ring of slightly enhanced density that each wave had built up over 380,000 years of travel, froze into the distribution of matter at that moment, and that distribution became the seed for the galaxy distribution we see today. The radius of those frozen ripples, how far the wave had traveled in 380,000 years before it stopped, works out to about 490 million light years. That's the scale of the ruler. It's not arbitrary. It's physics. The speed of sound in the early plasma, the temperature, the density, the duration, all deterministic, all calculable, all known from other measurements. We can figure out the true size of that ruler from first principles, from the physics of the early universe, without ever pointing a telescope at a galaxy. And that's the trick. That's the elegance that makes DESI's measurement possible. If you know the true size of a ruler in physical length, and you can measure how large it appears in the sky, you can calculate the distance to it with precision. Not approximately. Precisely the way surveyors use to triangulate distances using objects of known size at known angles. The further away a fixed-size object, the smaller it appears. Measure its apparent size, know its true size, and the distance falls out of simple geometry. This is what astronomers call a standard ruler, a cosmic measuring rod of known physical length. DESI finds this ruler at different redshifts, at different distances, therefore different epochs in time, and measures how large it appears in the sky at each epoch. The apparent size of the same physical ruler seen from different distances tells you exactly how far away you are from it. And if you measure its apparent size at many different redshifts, many different cosmic ages, you can build up a record of how the distance-redshift relationship evolved. Which is another way of saying you can map how the expansion rate of the universe has changed across time. Near galaxies with low redshift show you the expansion rate now, or close to it. Galaxies at moderate redshift, light that took 4 or 5 billion years to reach us, show you the expansion rate when the universe was middle-aged. Galaxies at high redshift, their light emitted 8 or 9 or 10 billion years ago, show you the expansion rate in the universe's youth. By looking across the full range, from nearby to the edge of the survey, from recent history to deep cosmic past, DESI doesn't take a single measurement of dark energy. It takes hundreds, thousands, spread across the full 11 billion years the survey covers. Each measurement is a frame in that film of the universe's expansion. Line them up in order, earliest to latest, and you can see how the expansion rate evolved. You can see whether dark energy was constant, providing the same push throughout, or whether it was different at different times, whether it was stronger in the ancient universe or weaker, whether it has drifted. That's the experiment. Not measure dark energy once. Measure it across time and watch whether it moves. The baryon acoustic oscillation signal, that 490 million light-year standard ruler, those frozen sound waves from the early cosmos, is the instrument's primary tool for doing this. BAO, as it's abbreviated. a frozen fingerprint of pressure waves that rocked the universe 380,000 years after the Big Bang. Preserved in the statistical distribution of where galaxies sit, readable by anyone patient enough and equipped enough to map enough of the sky with enough precision. Other telescopes have found BAO before. This is not a new technique. The signature was first detected in galaxy surveys in 2005, and it's been refined many times since. But DESI brings something new. Scale. 15 million galaxies across 11 billion years worth of look-back time, covering an enormous patch of the three-dimensional sky, measured with spectroscopic precision, each galaxy not just located, but redshift tagged to its exact moment in cosmic history. The sheer volume of data means the statistical bump that is the BAO signal can be measured not just at one redshift, but across many different redshift ranges, each range corresponding to a different era, each era a different chapter in the expansion's history. BAO tells you the expansion rate. Spread across 11 billion years of look-back time, it tells you how the expansion rate has changed. And there's something genuinely moving, if you let it land, about the fact that sound waves from the universe's infancy. Pressure waves that rippled through a hot plasma nearly 14 billion years ago, that froze when neutral atoms formed and the universe went transparent, that imprinted themselves on the positions of every galaxy that formed afterward, that those ancient, frozen waves are now being used by instruments on a mountain in Arizona to measure whether the force accelerating the cosmos today is the same force it was 8 billion years ago. Sound becoming a ruler, becoming a clock, becoming a verdict on the nature of dark energy. The universe left us a gift in its childhood. It just took us this long to understand how to read it. But DESI doesn't stop with BAO. The measurement is strengthened, and its meaning made more specific when the galaxy map is combined with independent data from two other sources. One is the cosmic microwave background, the CMB, the faint afterglow of light from those same 380,000 years after the Big Bang when the universe went transparent. That light has been traveling freely ever since. It fills the sky from every direction. And its tiny temperature variations, the Planck satellite measured them with extraordinary precision, and a ground-based instrument called ACT has added detail, encode enormous amounts of information about the early universe's composition, geometry, and expansion history. The CMB gives a precise measurement of the universe at a single early moment, like a photograph of the beginning. DESI's map gives a record of how things evolved afterward. Together they form a before and after, with billions of years between the frames. The other source is Type 1 supernovae, those same exploding white dwarf stars that Perlmutter and Schmidt and Ries used in 1998, the ones that started this whole story. They're still working, still being catalogued, still being measured, in their hundreds and now their thousands. The newest compilations, Pantheon Plus, Union 3, the Dark Energy Survey's 5-year collection called DESI-5YR, each represent years of careful observation and calibration and argument about how to properly account for variations in how those stars explode, how their light curves should be standardized, how to correct for the dust and distance and redshift that affect each measurement. Supernovae are a different kind of standard, a standard candle rather than a standard ruler. They provide a brightness measurement rather than an angular size measurement. They probe distance in a different way. But they probe cosmic expansion. The same cosmic expansion, and they reach out to different redshifts, different epochs, When BAO and CMB and supernovae are combined, when three independent probes, using three physically different methods, reaching different distances, calibrated from different physical principles, all agree on a measurement, the result carries a weight that no single method could bear alone. And that is exactly how DESI's analysis was conducted. Not with BAO alone, not with any one instrument's data, with all three carefully combined, each serving as a cross-check on the others. The CMB anchors the analysis in the early universe. BAO tracks the expansion across the middle billions of years. Supernovae add precision in the nearby universe and the intermediate range. Together they form a scaffold across 11 billion years of cosmic time, each supporting the others, each vulnerable to different systematic errors, each measuring from a different angle. Three completely different views of the same universe, assembled into a composite picture. And the picture they assembled when DESI published its first major cosmology results in April 2024. And then again, with greater precision in March 2025, told a story that did not line up with the standard model's prediction. Before the details of what the data found, it's worth staying a moment longer with what the data were looking for, because understanding the target makes the finding land harder. The standard model, Lambda-CDM, predicts a specific, smooth expansion history. Lambda is constant, so its influence on expansion should be constant. As you trace the expansion rate backward through time toward the universe's youth, you should find that dark energy's contribution to the expansion changes in a predictable way with the overall density of the universe, not because lambda changes, but because the relative contributions of matter and dark energy shift as the universe evolves. Early on, matter was dense enough to slow the expansion. Dark energy was always there, but smaller in proportion. Gradually, as matter diluted and dark energy held steady, dark energy came to dominate. The crossover from matter-dominated to dark energy-dominated expansion happened a few billion years ago. That crossover, that curve, that smooth transition. The standard model predicts its exact shape, and a constant dark energy with W exactly -1 traces a very specific path through parameter space, a path that DESI's data can follow. The question was whether the path the data preferred matched the path that W equals -1 would draw. It didn't. Not quite. To describe what the data preferred, the DESI collaboration used a more flexible model, not Lambda-CDM with its one fixed parameter. A model called W0-DM with two parameters instead of one, W0, which is the value of dark energy's equation of state today, right now, in the current universe, and WA, which describes how fast that equation of state changes over time. A rate of change. A drift. In Lambda-CDM, these two numbers are fixed. W0 equals -1, WA equals 0. No drift. No change, the constant case. What DESI's combined data, BAO plus CMB plus supernovae, found when fit to this two-parameter model is the thing that stopped people in their tracks. The data preferred W0 to be greater than -1, meaning dark energy is slightly weaker today than a cosmological constant would be, and WA to be negative, meaning dark energy was stronger in the past than it is now, and that it weakened as the universe aged. Stronger then, weaker now, and approaching weaker still. That's a drift, a trajectory, a direction, not just a different value, but a moving one. And the cosmological constant, W equals -1, forever and everywhere, is strictly forbidden from drifting. Not unlikely to drift, not assumed not to drift. Forbidden, mathematically, by the nature of what a constant is. You cannot have a constant that changes its value. The words contradict each other. If W has a var, if it has a rate of change that isn't zero, then whatever dark energy is, it isn't a constant. The behavior the data prefer is something specific. In the deep past, the data suggest dark energy had an equation of state below -1. Below -1 is called the phantom regime, a term that means the dark energy density was actually increasing faster than the volume of space, something even more exotic than a cosmological constant. Something that no straightforward physical field can do without violating certain energy conditions physicists generally consider sacred. Dark energy apparently dipped into that territory long ago, then rose back up, crossing through -1 and continuing upward toward the present day, where it sits slightly above -1, slightly weaker than a constant, slightly less able to push. Lambda is pinned at -1. It cannot dip below and cannot rise above. It sits at the line. Permanently, the data prefer a path that crosses that line, a trajectory that goes from below to above, passing through -1 as it climbs. That crossing is the detail that makes it so clean a contradiction. A constant doesn't cross anything. A constant sits still and watches everything else move. A dark energy that crosses the -1 line, that was phantom in the past and is something else now, is by definition not a constant. This is the specific thing the data found. Not just dark energy might be changing. A particular direction, strengthening in the past, fading now, on a trajectory the standard model has no room for. And the question hovering over all of it, the question that keeps this in the realm of hints rather than discovery, the question DESI's collaboration has been careful and explicit about, is whether the data are strong enough to trust that conclusion. Whether the signal is real or whether it's a ghost in the numbers, a trick of incomplete data or imperfect calibration or ordinary statistical noise that happened, this time, to fall in an interesting place. That question has a formal answer. A number. A number that the entire field uses as a threshold for believing what it sees. And the number the data came back with sits in a very particular, very uncomfortable position, high enough to be impossible to ignore, not quite high enough to be impossible to doubt. You don't have to know exactly what that number is to feel the weight of where it sits. But soon you will, because where it sits is exactly the place where cosmology is holding its breath, where the equipment is running, the data are mounting, and everyone who has spent their career on these questions is watching a single number and waiting to see which way it moves. The number is called sigma. You might not have heard it before, or you might have, a long time ago, in a statistics class or a science documentary, where someone mentioned it in passing and it felt like jargon, like a thing you were supposed to already understand. But it isn't complicated, not really. Sigma is just a way of asking how surprised you should be. It's a way of measuring how far a result sits from what you'd expect, if nothing interesting were happening at all. The further a result sits from ordinary, the higher the sigma. And the physics community, over generations of working through particle colliders and radio telescopes and spectrographs and supercomputers, has settled on a very specific number as the line between interesting and real, between worth talking about and worth believing. That number is 5. 5 sigma is the threshold. 5 sigma means the result you're seeing would occur by random chance about once in every 3.5 million tries, 1 in 3.5 million. When physicists say they've discovered something, a new particle, a new force, a new feature of reality, 5 sigma is where that conversation starts. Below 5, you have anomalies, hints, possibilities, things worth watching. Above 5, you have facts worth building on. The DESI result, the one that has cosmology quietly unsettled, the one that says the universe's dark energy may have been stronger in the past and may be easing its grip on the present, that result, depending on how you calculate it, sits somewhere between 2.8 and 4.2 sigma. Let that settle for a moment. Above 3, possibly almost 4. Close to 5, but not 5. And that gap, that single sigma of distance from the line, is exactly where the tension lives. Exactly the place where a discovery that could rewrite the predicted end of the universe sits in the uncomfortable middle, real enough to take seriously, uncertain enough that no one is ready to say so out loud. To understand how the number got there and why it matters that it sits where it does, we need to go back to the beginning of what DESI actually found. Not the summary, not the headline, the data itself. The first results came in April of 2024. The collaboration called it DR1, Data Release 1, and it covered the analysis of roughly 6 million galaxies and quasars, 6 million objects with known positions in three-dimensional space, sorted by redshift. Organized into layers of cosmic time, each one a data point in the largest survey of its kind, yet completed. 6 million sounds like an enormous number, and it is. A human being, counting one per second, would take nearly 70 years to count to 6 million. But the universe contains something like 2 trillion galaxies, and 6 million is a very small fraction of that. A sample, a careful, deliberate, scientifically structured sample, but a sample nonetheless. Still, 6 million data points, spread across billions of light-years, organized into the distribution of matter across cosmic history, is enough to start saying something meaningful about the expansion rate. It's enough to build a map that earlier generations of astronomers would have found staggering. And when DR1's data were analyzed and combined with other measurements, the kind of triangulation DESI's team has been careful to do from the beginning, the signal appeared. But the collaboration didn't stop there. They kept collecting. The instrument kept running, those 5,000 robotic positioners rotating and reorienting through the nights at Kitt Peak. The light from distant galaxies flooding down into fiber optic cables thinner than a human hair, each one carrying the spectral signature of a world billions of light years away. And by early 2025, they had enough for DR2. Data Release 2, announced in March of 2025, covered nearly 15 million galaxies and quasars. Not 6 million, 15 million. Across roughly 11 billion years of cosmic history. The largest three-dimensional map of the universe ever made, at the time it was published. You could try to picture it, a structure so vast and detailed it makes the 6 million object first release look like a rough sketch, and the honest answer is that no human mind can really hold it. 15 million points of light, each one a galaxy with hundreds of billions of stars, each one positioned at a precise distance and epoch, each one a sample of the universe as it existed at a specific moment billions of years ago. The whole thing is more like a geological record than a photograph. It's a core sample drilled through cosmic time. And in that core sample, the signal was still there. Larger now, more detailed, but the same basic shape. The universe's expansion rate, watched across 11 billion years, did not behave the way a constant dark energy would have it behave. To understand exactly what the data found, it helps to know the model the collaboration used to describe it. Because the cosmological constant, the lambda in Lambda-CDM, that fixed number locked to -1, is technically a special case of a more general framework. Physicists have a more flexible version, a model that doesn't assume anything is constant, that lets the data itself tell you whether dark energy changes over time. It's called Lambda-CDM. The name is dense, but the idea is simple. Instead of assuming dark energy's character is always and forever described by a single fixed number, W0YACDM uses two numbers. The first is W0, dark energy's equation of state parameter right now, today, in the current universe. The second is Y, a number that describes how quickly and in what direction that parameter changes over time. In Lambda-CDM, the standard model, the answer to both questions is already known before you look. W0 equals -1, exactly. Y equals 0, exactly. Those two values sit there fixed, like a fence post in concrete, and everything the model predicts flows from them. The fate of the universe, the expansion rate through cosmic time, the structure of the galaxy distribution, all of it rests on those two numbers being exactly what they are. What DESI found when it applied the W0CDM framework to its data, when it let the measurements speak rather than assuming the answers in advance, is that the data prefer different values. Not wildly different, not by enormous margins, but different in a specific, directional, physically meaningful way. The data prefer W0 to be somewhat greater than -1. Not less than -1. Greater, which means right now in the present universe, dark energy's pressure to density ratio is weaker than a cosmological constant would be. Its grip on space is looser now than it would be if lambda were truly constant, and the data prefer Y to be negative. Which means the parameter has been moving, not staying fixed at -1, but changing over time, shifting, evolving. A -Y means that in the past, the parameter was lower, further below -1. Deeper into what physicists call the phantom regime. Phantom, it's a strange word for a physical concept, but it captures something real. When the equation of state parameter dips below -1, dark energy takes on properties that push beyond what ordinary fields or fluids can do. It becomes, in a technical sense, more extreme than a cosmological constant, a stronger, stranger push, one that violates certain energy conditions physicists had assumed were inviolable. The phantom regime is, in the language of the field, an unusual and uncomfortable place for anything to live. And yet, the data say that in the deep past, dark energy was there, below -1, in the phantom. And that since then, since those earlier epochs of the universe's life, the parameter has been rising, climbing, moving from phantom territory below -1, upward through the line, past it, into the region above, where W0 now sits. Higher than -1, weaker now than it used to be. This is the forbidden move. This is the specific behavior the cosmological constant cannot perform, by definition, by mathematics, by the meaning of the word constant. The constant cannot cross a line. It cannot be below something in the past and above something now. It doesn't move. It is, in the most literal sense, the one thing in the universe that was supposed to just sit there. And the data are saying it moved. Now, here is where the careful telling matters. Here is where the science, the actual science, insists on something more honest than a clean narrative. The signal doesn't come from any single measurement. It doesn't come from DESI's galaxy map alone, from those 15 million objects arranged in their three-dimensional structure. If you look at the galaxy map by itself, the signal from BAO alone, from those frozen baryon acoustic oscillations, those ancient sound wave imprints, the hint of evolving dark energy is interesting, but modest. You need more. You need convergence. What DESI did, what the collaboration has been systematic and transparent about, is combine three distinct, independent lines of evidence. Three separate telescopic windows into the universe's history, each using a different physical mechanism to probe the expansion rate. Each developed by different teams with different instruments and different sources of potential error. The idea is that if three independent methods all point the same direction, the chance that all three are wrong in the same way, at the same time, shrinks dramatically. The first is the galaxy map itself, the bow signal, the standard ruler, the measurement of how that 490 million light-year frozen scale in the galaxy distribution appears to different sizes at different redshifts, translating those apparent sizes into expansion rates across 11 billion years of history. The second is the cosmic microwave background, the CMB, that faint glow of ancient light, the afterimage of the universe at 380,000 years old, when it first became transparent and photons were set free to travel unimpeded through space. The CMB has been mapped with extraordinary precision by satellites like Planck and ground-based telescopes like the Atacama Cosmology telescope, known as ACT. It constrains the early universe's physics with almost terrifying accuracy. It tells us what the universe looked like at its beginning, and from that starting point, we can calculate what it should look like now, and compare that prediction to what DESI finds. The third is Type 1a supernovae, those exploding white dwarf stars, those standard candles whose known brightness lets us calculate their distance and compare it to how fast space has carried them away from us. The same kind of observation that Perlmutter and Schmidt and Ries used in 1998 to discover dark energy in the first place. The same technique, now vastly improved, applied to a vastly larger sample of supernovae stretching across a vastly wider range of cosmic time. When all three point the same direction, when galaxy maps and ancient light and exploding stars all prefer the W0A CDM values over the Lambda-CDM ones, the combined signal is what gets published. And the combined signal is what gives the DESI result its weight. But there's a complication. And it's the complication that keeps the result below 5 sigma, that keeps it in the uncomfortable middle, that keeps cosmologists choosing their words very carefully when they describe what the data say. The three supernova samples don't fully agree. Type 1a supernovae are the most powerful distance indicators humans have found in the universe. But they're not quite as perfectly calibrated as physicists would like. Different research teams working with different telescopes and different calibration strategies and different statistical methods have assembled different compilations of supernova data. And those compilations, when fed into the DESI analysis, produce somewhat different answers. There are three major compilations in the current analysis: Pantheon Plus, Pantheon Plus, a large catalogue assembled from multiple surveys, well-established and widely used. Union 3, another compilation with different calibration choices and a somewhat different source selection. And SN5YR, the Dark Energy Survey 5-year supernova sample, the most recent major compilation, assembled from 5 years of observation by the Dark Energy Survey camera. When DESI's galaxy map is combined with the CMB and Pantheon Plus, the significance of the evolving dark energy signal comes out around 2.8 sigma. When the same galaxy map and CMB are combined with Union 3, the significance is somewhat different, and when DES SN5YR is used instead, the significance climbs to about 4.2 sigma, 2.8 to 4.2. all from the same fundamental galaxy survey, the same CMB data, the same underlying physics, but with different supernova catalogues slotted in. The spread is a window into how much the supernovae are doing. They're doing a lot. The galaxy map and the CM constrain many things, but the supernovae, the way they're calibrated, the way their distances are calculated, the specific set of them that gets included, those choices move the needle by more than a full sigma on their own. This is not a scandal. It's not an accusation that someone's data are wrong. It's how science works when you're at the frontier, when you're trying to extract a faint signal from an enormous dataset using instruments and methods that are themselves being refined in parallel with the analysis. But it is a reason for caution. A reason why the DESI collaboration, from the moment the results were published, has been consistent and deliberate about what they're claiming and what they're not. 3 sigma in the physics world is what you call evidence. Not discovery, evidence. A 3 sigma result means the chance of it being a random fluctuation is roughly 1 in 370. Which sounds conclusive until you realize that across all the measurements physicists have made, across all the papers that have been published, across all the anomalies that have been noticed and tracked and followed up on over the decades, 3 sigma results have appeared and then disappeared with uncomfortable regularity. They are, in the lived experience of the field, not safe. They are interesting. They are worth taking seriously. They are sometimes the first glimpse of something real, but they have also been traps. 5 sigma is what you call a discovery, 1 in 3.5 million. That's the level where the community will say, collectively and without significant dissent, yes, this is a real feature of the universe, this is a fact. 5 sigma is where the Higgs boson was confirmed in 2012. 5 sigma is where new particles get named and Nobel committees start paying attention. The DESI result, 2.8 to 4.2, depending on which supernova you use, is above 3, often well above 3. In the DR2 analysis, using DESI 5YR, it's flirting with 4.5. And 4.5 sigma is genuinely extraordinary. It's a level of significance that would, in almost any other context, prompt serious celebration. 4.5 sigma of evidence that the force governing the fate of the cosmos has not been constant. That the bedrock assumption of 25 years of cosmological modeling has a real data-backed crack in it. And yet, 4.5 is not 5. And the fact that the number changes by more than a full sigma depending on which supernova you trust, the fact that the level of certainty is this sensitive to a calibration choice, is itself information. It's the universe's way of saying that the tool we're using to probe it isn't yet sharp enough to give a clean verdict, that we're close to the answer but not quite touching it. This is what the phrase quiet panic really means. Not that cosmologists are running in circles or refusing to do their jobs. They're doing exactly the right things, publishing, scrutinizing, being transparent about the sources of uncertainty, talking openly about what the failure modes are and what more data would resolve. The panic, such as it is the private existential sensation of watching a pillar tremble, of having a number approach the line, increment by increment, dataset by dataset, and not quite reaching it. Of knowing that the number could go either way from here, could rise to 5, crossing the threshold and rewriting the textbooks, or could fall back as better calibrations and larger samples come in, leaving the cosmological constant untouched and the last 25 years confirmed. That sensation, so close, not there yet, watching and waiting, has a particular quality that is hard to describe outside the experience. It's a little like standing at a window in winter, watching a thermometer, knowing that at some point in the next few hours, either the rain will turn to snow or it won't, and the world will look completely different in the morning if it does. You can do nothing but wait. The data will accumulate or they won't. The signal will sharpen or it will dissolve. And until it does one or the other, every conversation about the future of the universe has a conditional at its center that cannot be removed. DR1 in 2024 saw 6 million galaxies tell a story. DR2 in 2025 saw 15 million tell essentially the same story, with more detail and more confidence. The signal held, grew, strengthened. Each additional galaxy is a vote. 15 million votes, organized across 11 billion years of cosmic time, are saying something consistent. The universe's expansion does not match what a perfectly constant dark energy would predict. And the W0-way CDM model, with its 2 parameters, fits the data better than Lambda-CDM does. Not by an enormous margin, the improvement is real but measured, but it fits better. The data, when you let them choose between the 2 pictures of dark energy, the locked, frozen constant and the slowly evolving field, prefer the one that moves. The specific corner of parameter space they prefer is the one lambda is not allowed to enter. W0 greater than -1, Wa negative. Those 2 values together describe a dark energy that was phantom in the past, stronger than the constant, deeper into that unusual territory below -1, and has been rising since, weakening, climbing through and past the -1 line into the present, where it sits today with a value somewhat above where the cosmological constant lives. A constant cannot do this. A constant cannot have been in one place and now be in another. By definition, by the mathematics, by the physics of what a cosmological constant means. The data are not pointing at a variation on lambda. They are pointing at something that, if they are right, is not lambda at all. What it might be is a question with a long and interesting answer that the next part of this conversation will reach in time. But for now, for this moment in the telling, it's enough to sit with the shape of it. 15 million galaxies. 3 independent lines of evidence, a signal between 2.8 and 4.2 sigma, depending on how you weigh the supernovae. A number climbing toward a threshold, not yet there, hovering. The CMB, that ancient light, that afterimage of the infant universe, anchors the analysis at the beginning of time. Planck mapped it with extraordinary precision. ACT has refined specific aspects of that map. Together, they tell you what the universe was doing at 380,000 years old, and from that starting condition, you can calculate a trajectory, a prediction for how things should look at every point since. The CMB data, by themselves, are consistent with Lambda-CDM. They don't demand a changing dark energy. They are compatible with it, but they don't require it. That's an important distinction. The CMB is not the source of the signal, it's the anchor. When you combine the CMB's early universe constraint with DESI's mid and late universe galaxy map, you're asking, given what the universe looked like at 380,000 years old, and given what it looks like now, is the path between those 2 snapshots the path a constant dark energy would take? And the combined answer, galaxy map plus ancient light, says, not quite. The supernovae then add the 3rd dimension. They probe intermediate epochs, filling in the timeline between the CMB's deep past and DESI's later observations. They measure distance directly, comparing the known brightness of exploding white dwarfs to their apparent brightness in the sky, using that gap to calculate how far away they are, and therefore how the universe expanded at the moment of each explosion. Different supernovae at different redshifts tell different chapters of the expansion story. And the story they tell, when stacked together and combined with the galaxy map and the ancient light, is a story in which the expansion rate through cosmic time bends in a specific way, a way that is hard to explain if dark energy is constant. The disagreement between Pantheon Plus and Union 3 and DESI 5YR isn't about whether the bending is there. All three samples see the same basic pattern. The disagreement is about how sharp the bend is, how pronounced the deviation from the Lambda-CDM prediction. That's what moves the sigma. The direction is the same. The magnitude is disputed. And disputed magnitude, when the thing you're measuring is already near but not at the threshold, is what keeps the result in the uncomfortable middle. The DESI collaboration has been explicit about this. The people who built the instrument, who designed the fiber positioners and the spectrograph and the pipeline that converts raw photons into galaxy positions and redshifts, they are the ones saying, clearly and publicly, that they are not claiming a discovery. They are calling the result hints. Tantalizing. Worth watching. They have been careful with their language in a way that, in a different field or a different era, might read as false modesty. But it isn't false modesty. It's the appropriate response to extraordinary stakes. Because the extraordinary nature of the claim, if it's true, demands an extraordinary standard of proof. 25 years of cosmological modeling rest on the cosmological constant, thousands of papers, dozens of major surveys. The entire framework that lets physicists make predictions about galaxy clustering, about the large-scale structure of the universe, about the growth of dark matter halos and the formation of clusters, all of it incorporates lambda. Overturning it isn't a tweak. It's a renovation of the foundation. And foundations don't move because of a 4 sigma whisper in the data. Not in physics. Not responsibly. What a 4 sigma whisper does is tell you to look harder, build more, check everything. What it does is send telescopes back to the sky with clearer instructions and sharper tools. What it does is cause the entire community to lean forward, very carefully, and say, let's see if this is still there when we have twice the data, twice the confirmation. A second independent instrument saying the same thing from a completely different direction. Because that's how physics actually works. Not with a single dramatic announcement and a press release. With accumulation. With layering. With the slow, unglamorous, methodical addition of evidence until the signal is no longer deniable, until the sigma crosses 5, until the result is so robust that no reasonable alternative explanation remains. The discovery of dark energy itself followed this path, hints in the mid-90s, 2 competing teams racing toward confirmation, and then in 1998, a result strong enough, consistent enough, unexpected enough, that the community had to accept it even though it violated virtually every prior expectation. Even that took years of subsequent confirmation before the Nobel Committee was satisfied. The DESI result is sitting at the beginning of that process, not the end. It's sitting at the point where hints become evidence, becomes proof, and the question is simply how much further the signal will travel. 3 sigma is evidence. The data, in their least favorable configuration, using Pantheon plus supernovae, give about 2.8 sigma. Using the most favorable configuration, DESI 5YR, they give about 4.2, possibly pushing toward 4.5 in some analyses. The midpoint of that range is somewhere in the low to mid-3s, comfortably above 2. comfortably below 5. What lives in that space is not certainty. What lives there is the peculiar scientific condition of being unable to look away. If this were 2 sigma, 1 in 20 chance of a fluke, you'd note it and move on. The field produces 2 sigma anomalies regularly, and most of them evaporate. But 3.5, 4 sigma of evidence that the dominant component of the universe is not behaving as advertised, that doesn't evaporate easily. That lodges. That sits in seminars and coffee conversations and late-night calculations and doesn't let go until it either resolves to a confirmed discovery or reveals its own flaw. There's a particular kind of alertness that cosmologists carry right now. Not panic in the dramatic sense, more like the quiet, sustained attention of someone who has noticed something out of the corner of their eye and is trying, carefully, not to startle it before they can get a good look. A measured watchfulness. An awareness that the next data release, the next independent analysis, the next instrument coming online could shift the picture significantly in either direction. And the funny thing, the thing that makes this moment genuinely unusual, even within the long history of anomalies and almost discoveries in physics, is that 15 million galaxies, the largest map of the universe ever made, is not the final word. It's the beginning of the final word. The survey isn't done. The instrument is still running. The fiber positioners are still reorienting through the Arizona nights, still capturing spectra, still adding galaxies to the count, one night at a time. The target for the full survey is 40 million or more than twice what's been analyzed so far, and that analysis hasn't been done yet, which means the signal will either hold and strengthen as more galaxies fill in the map and the statistics grow more powerful, or it will begin to flatten out, the bump in the data smoothing away as the sample grows, and the unusual cluster of points that gave rise to the hint turns out to have been an ordinary fluctuation wearing an interesting costume. That question, hold or flatten, has no answer tonight. It has no answer yet, but it will, within years. Within the arc of time that the people who built DESI designed the instrument to span. They set out to do a 5-year survey. They are still inside that survey. The verdict is in progress. And DESI isn't the only one looking. But that part of the story, the reinforcements, the independent instruments, the other eyes that will turn to this question and give their own verdicts, that part belongs to what comes next. For now, rest with this piece of it, the map itself, the numbers it returned, the particular value of sigma that sits like a stone in the middle of the road between assumption and discovery. 15 million galaxies said something. 3 independent methods of measuring the universe agreed on a direction, disagreed on a magnitude. The signal sat at somewhere between 2.8 and 4.2 sigma, depending on how you weigh the evidence. 3 sigma is called evidence. 5 sigma is called discovery, and the result is there, in the middle, alive and unresolved and impossible to dismiss, the kind of number that doesn't let the field sleep easily and probably shouldn't. The full shape of what DESI found is now in your hands, the map, the model, the forbidden move across the -1 line, the convergence of 3 probes, the disagreement that keeps the result honest, and the threshold that hasn't quite been crossed. That's the data, that's the measurement, in its full texture. What those numbers mean for the universe's ending, for the standard model, for the theories waiting in the wings, and for the instruments now being aimed at exactly this question, that part is still ahead of you, somewhere in the long quiet of this night. So let's think about the ending, not the end of this story, the end of the other one, the bigger one. The one that started nearly 14 billion years ago in a flash of heat and light and energy so concentrated it beggars every analogy we reach for. The one that has been running ever since, expanding outward, cooling as it goes, growing galaxies and stars, and in at least one quiet corner. People lying in the dark, wondering how it all finishes. For a long time, for the 25 years since 1998, when the accelerating universe announced itself through those dimmer-than-expected supernovae, physicists had a fairly confident answer about the ending. Not a certain answer, never that, but a well-supported, mathematically clean, almost aesthetically satisfying one. And it went like this. The cosmological constant, lambda, is constant. Its value is fixed. Its push does not weaken as the universe grows, it does not strengthen either. It simply is, woven into empty space itself, a property of the vacuum as fundamental and unchanging as the speed of light. And because it is constant, and because the universe is expanding, and because the density of everything else, matter, radiation, all the stuff that gravity clings to, dilutes as that expansion carries things farther apart, there comes a point where the constant push wins decisively and permanently. There is no catching it. There is no mechanism by which it could be overcome. The result, projected forward over timescales that make the current age of the universe look like a warm-up act, is the Big Freeze, sometimes called heat death. The name varies, the picture is the same. Galaxies beyond our own local group, the small family of galaxies bound to us by gravity, drift beyond the horizon of what we can ever reach or even see, carried away by the expansion too fast for light to bridge the gap. The Milky Way merges with Andromeda, and the combined result floats alone in an increasingly empty and dark universe, a single island of matter in a sea of stretching space. Stars form and burn and die, and the gas to make new ones slowly runs out, and over trillions of years the lights go out one by one. Black holes evaporate through the slow quantum process Stephen Hawking described, and eventually, over timescales written in powers of 10 so large, they stop feeling like numbers and start feeling like poetry. Everything approaches maximum entropy, maximum disorder. The coldest, darkest, most spread out state the laws of physics allow. Nothing happens anymore, because nothing has the energy to make anything happen. The universe just drifts, silent and enormous and spent. It is, in its way, a peaceful ending. Slow, inevitable, certain, if the cosmological constant holds. That if is the thing that just got interesting. Because what DESI's data prefer, what the map of 15 million galaxies, layered on top of the cosmic microwave background and the light curves of Type 1a supernovae, whispers when you ask it the right question, is that the constant might not be constant. That the thing driving expansion was stronger in the deep past and has been easing since. That the equation of state parameter W, which everyone has been measuring as pinned at -1 for a quarter century, may be on the move. Rising, coming up from somewhere below that line, crossing it, pulling away from it in the recent universe. If that is true, the picture above needs to be redrawn. Think about what a weakening dark energy actually means in physical terms. The cosmological constant pushes because it is a property of space itself. Every new cubic inch of space that expansion creates comes preloaded with the same energy density, so the total push grows as volume grows. It cannot weaken because it is not running down. It has no reservoir to drain. But a dark energy that changes, that has an equation of state parameter that evolves, is different in kind, not just in degree. It is not a property baked into the vacuum. It behaves more like a field, something that has a value, and that value can shift the way a field in physics generally can. And a field that was stronger before and is weaker now could, in principle, keep going, could keep weakening, could, if the trajectory continues far enough, fade to the point where it no longer overcomes gravity at cosmic scales. At that point, the expansion slows. It does not just slow down its acceleration. The universe would already be doing that if dark energy were simply weaker than before. It could slow down in absolute terms. And if gravity reasserts itself across the largest scales, the expansion does not go on forever. It stops. And reverses. What comes after reversal is a universe that contracts. Galaxies that are currently fleeing each other begin, over unimaginably long timescales, to fall back together. The cosmic web tightens instead of stretching. Structures that took billions of years to form get compressed. And if the contraction continues, if there is nothing to stop it, the universe ends not in cold and dark and silence, but in heat, in density, in a kind of violent reversal of its beginning. Cosmologists call this the Big Crunch, the point at which everything that expansion spread apart over 14 billion years is driven back together into something so hot and so dense that the physics we use to describe the ordinary universe breaks down entirely. Between the Big Freeze and the Big Crunch, there is an enormous range of possible fates that nobody has a clean map of. Dark energy could weaken and level off, plateau somewhere above zero, still pushing, just less vigorously, and the universe might expand forever, but more slowly, producing a different kind of heat death, dimmer and slower, but still there. Dark energy could oscillate. It could flip sign and become attractive rather than repulsive, leading to its own exotic variants of collapse. There are models in the literature for most of these, and all of them hinge on the same underlying question: what exactly is this field, and what determines how its value evolves? The point for right now in this quiet is simpler than all of that. The point is that the ending of the universe is not settled. It is downstream of a number, the equation of state parameter, W, and its rate of change, y, that physicists thought they already had pinned down, thought they knew. The signal DESI returned said, "You may not know it as well as you thought." And if the signal holds, everything written in the past 25 years about the long-term fate of the cosmos needs at minimum a footnote, and at maximum a substantial revision. The stakes, in other words, are about as high as stakes get when you are talking about things that are not going to affect anyone alive or anyone their children will ever know. And yet it matters, somehow, it matters the way all deep future cosmology matters. Not practically, not urgently, but in the way that knowing the shape of the story you are part of matters, even when you will not be around for the last chapter. Now, here is where the good honest reckoning has to happen. Because the data say what they say, and what they say is interesting and important, and has physicists paying very close attention. But the data do not say, "This is confirmed." The data do not say, "We know." The data say, "Here is a signal. Here is a direction. Here is a number that is not where it used to be thought to be. And here is our best current estimate of how surprising that is." And that estimate, 4 sigma at its strongest, 2.8 sigma at its weakest, depending on which supernova dataset you trust, is not the 5 sigma that separates a hint from a discovery. And that gap is not a formality. It is not bureaucratic caution dressed up as science. It is the field honestly accounting for the very real ways this result could still dissolve. Let's go through them, because they deserve to be held clearly. The first is the one that shows up most visibly in the numbers themselves: supernova calibration systematics. The 3 supernova datasets, Pantheon Plus, Union 3, and the Dark Energy Survey's 5-year compilation, DESI SN5YR, don't all agree on how strong the signal is. DESI SN5YR pushes the combined significance up toward 4.2 sigma. Pantheon Plus keeps it closer to 2.8. That spread is not small. It is not a rounding error. It is a spread that reflects genuine uncertainty in how you take a Type 1a supernova, which is already an approximation of a standard candle, a physical process that doesn't produce perfectly identical brightness every time, and calibrate it well enough to use as a precise cosmic ruler across billions of light years. Type 1a supernova are what made the 1998 discovery possible. Saul Perlmutter's supernova cosmology project and Brian Schmidt and Adam Reis's High-Z supernova search team both used them. The idea is that these explosions, a white dwarf star accumulating mass from a companion until it crosses a critical threshold and detonates, are similar enough in their peak brightness that you can use the difference between how bright they appear and how bright they ought to be to infer how far away they are, and from there, what the expansion rate was when their light left. It is an extraordinary tool. It earned a Nobel Prize in 2011. But it is not a perfect tool. White dwarfs vary. The environments they explode in vary. The methods used to correct for that variation and standardize the candles have improved enormously over 25 years and are still improving. Subtle errors in those corrections, or systematic differences between the surveys in how they process and categorize supernovae, can shift the inferred expansion history in ways that look like a cosmological signal when they are really a measurement artifact. The disagreement between Pantheon Plus and DESI SN5YR is a flag that this particular uncertainty has not been fully resolved. It is not evidence of error. It is evidence that the measurement is hard, and hard measurements deserve the full 5 sigma before the textbooks change. The second honest failure mode is in the bow modeling itself. DESI's baryon acoustic oscillation measurements are extraordinarily precise. The 5,000 robotic fiber positioners on the Nicholas U. Male telescope, capturing 5,000 galaxy spectra simultaneously, retargeting in seconds. The engineering behind the data collection is remarkable, and the statistical power of 15 million galaxies is real. But the models used to extract cosmological parameters from that data involve assumptions about how galaxies cluster, about how the bow feature smears and shifts as structure forms over billions of years, about non-linear effects that are difficult to calculate from first principles and have to be approximated. If any of those modeling assumptions are subtly off, they could introduce a systematic preference in the inferred parameters, a bias that does not vanish with more data because it is baked into the analysis pipeline. The DESI collaboration has worked hard to test for this. They have run blind analyses where the team didn't know the cosmological result until the analysis was frozen, specifically to guard against unconscious tuning toward a preferred result. They have checked their pipeline against simulations. They are careful, competent people doing rigorous work. But they are the first to say that an independent analysis of the same data or the same analysis applied to an independent dataset is a necessary part of confirming what they found. The third failure mode is the simplest and most fundamental: statistics. Even a 4 sigma result has a chance, small but not negligible, of being a fluctuation. Cosmology has a long memory of anomalies that looked like signals and weren't. The 3 sigma bump that appeared in particle physics data and disappeared when the dataset grew. The hints of non-Gaussianity in the early cosmic microwave background maps that smoothed out with better instruments. The history of the field is partly a history of tantalizing signals that the universe eventually explained away with more patience and more precision. Not always. Cosmic acceleration itself, the very discovery DESI is refining. Started as a 2 sigma anomaly in 1998 and is now one of the most securely established facts in physics. But the base rate of 3 and 4 sigma claims, resolving as real versus as flukes, is sobering enough that the field insists on 5 before it calls anything settled. These are not reasons to dismiss DESI's results. They are the reasons the DESI collaboration itself has been clear and consistent. This is a hint. Tantalizing, the strongest hint we have. Not a discovery. The language the collaboration leaders have used publicly, intriguing, hints, requiring more data, is not hedging or corporate communications caution. It is the scientific method doing exactly what it is supposed to do. Extraordinary claims require extraordinary evidence. Overturning a 25-year pillar of the standard model, the cosmological constant that anchors Lambda-CDM, is about as extraordinary a claim as modern cosmology has in it. The evidence needs to be extraordinary in kind. It is getting there. It is not there yet. And while it is getting there, it is worth knowing that there are theories, real theories, developed long before DESI took its first spectrum, that would be vindicated rather than surprised if dark energy turns out to vary. The leading class of them goes by a name that carries a certain elegance: quintessence. Named after Aristotle's fifth element, the ethereal substance he imagined filled the heavens beyond the 4 terrestrial elements of Earth: water, fire, and air. In modern physics, quintessence is a hypothesized, slowly evolving scalar field, a kind of energy distributed through space that has a value which changes over cosmic time. It predates DESI by decades. Theorists invented it as a way of addressing a deep puzzle in the cosmological constant itself, not the question of whether lambda varies, but the question of why it has the value it does, which turns out to be one of the most embarrassingly difficult problems in theoretical physics. If dark energy is quintessence, if it is a field slowly evolving, stronger in the past and weakening now in precisely the way DESI's data prefer, then the W0R-CDM model is not just a convenient parameterization, it is a window into the physics of that field. The values of W0 and WAR encode how quickly the field is rolling down its potential energy landscape, and measuring them with enough precision to distinguish them from -1 and 0 would be, in effect, the first direct detection of a new fundamental field in nature. The kind of discovery that reshapes not just cosmology, but particle physics and quantum field theory. That is the scale of what is on the table, and why the field is paying such close attention. There is also the matter of a second crack in the standard model, one that has been sitting there, unresolved, for years, and that intersects in complicated ways with everything DESI is measuring. It is called the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding today, in technical terms, how quickly galaxies recede from us per unit of distance. You can measure it in 2 completely different ways. You can start from the very early universe, from the cosmic microwave background, the afterglow of the Big Bang captured by satellites like Planck, and use the physics of that early hot plasma to predict what the expansion rate should be today. Or you can go out into the local universe and measure directly, take nearby galaxies, find standard candles in them, build a distance ladder rung by rung, and read off the expansion rate from observation. Both methods are extraordinarily precise. Both methods are extremely well tested. They give different answers. The local direct measurement comes out higher than the early universe prediction by somewhere between 4 and 6 sigma depending on the analysis. That discrepancy has not gone away as measurements have improved. If anything, it has sharpened. And it does not have a clean, agreed-upon explanation. Some physicists hope that a dynamical dark energy, a quintessence field that was behaving differently in the early universe than it does today, could provide a piece of that explanation. A changing dark energy changes the expansion history, and a different expansion history changes the predicted value of the Hubble constant. Maybe, some argue, the Hubble tension and the DESI signal are related. Two manifestations of the same underlying physics that the cosmological constant, with its rigidity, cannot accommodate. Others warn that it is not so simple. Adding a varying dark energy to relieve the Hubble tension can sometimes make other tensions worse. Cosmology has several of these unresolved discrepancies sitting alongside each other. Sigma 8 tension, the S8 parameter describing how clumpy the universe is on large scales, also shows mild disagreement between different probes. And a proposed solution that fixes one while breaking two others is not a solution. It is a complication. The honest position is that the Hubble tension and the DESI result may be connected, may be independent, or may turn out to point toward different new physics. We do not yet know. What we do know is that Lambda-CDM is under stress from more than one direction, and that stress is accumulating. The standard model has been remarkably successful. It is important to say that clearly, because sometimes, in the excitement of a new anomaly, the model's achievements get lost. Lambda-CDM predicted the large-scale structure of the universe, the way galaxies cluster into filaments and walls and voids, with extraordinary accuracy. It predicted the acoustic peaks in the cosmic microwave background to high precision. It gave us a framework for understanding the history of the cosmos that has been tested against dozens of different observations and passed essentially all of them. It is not a model that is failing. It is a model that may be reaching the edge of its domain. The way Newtonian mechanics was not wrong about billiard balls and planets, but did require Einstein to extend it when things moved close to the speed of light. What DESI is doing with its 15 million galaxies and its 11 billion years of cosmic history mapped in 3 dimensions is not tearing down a bad theory. It is, potentially, finding the crack where the next theory begins. And that is different. That is how physics progresses, not in moments of pure destruction, but in moments where precision measurement finds the place where the current best model's prediction and the universe's actual behavior stop perfectly matching. And someone has to go figure out why. So where do we go from here? What resolves this? The answer is more data, more precise data, from more independent instruments. And some of those instruments are already running or already in the sky. DESI is right now still in its 5-year survey. The results released in 2024 and 2025, DR1 with roughly 6 million galaxies and quasars, DR2 with nearly 15 million, are not the final product. They are interim releases from an instrument that when its full survey is complete. aims to have mapped more than 40 million galaxies and quasars across the sky. The full dataset will be substantially larger than anything released so far. More data from DESI alone will sharpen the W0 and WAR constraints, reduce the error bars, and make it clearer whether the signal continues to grow or begins to shrink back toward the cosmological constant. There is also the Euclid Space Telescope. Launched by the European Space Agency in July of 2023, Euclid is a dedicated dark energy mission operating from space, outside Earth's atmosphere, with a wide-field camera designed to survey billions of galaxies across an enormous fraction of the sky. Its approach is complementary to DESI. It can map fainter and more distant galaxies in certain wavelengths. It measures galaxy shapes as well as positions to use weak gravitational lensing as an additional probe, and it does all of this from an orbit that sidesteps the atmospheric distortions that ground-based instruments have to correct for. Euclid is an independent instrument. It uses different methods and different systematic errors. If it sees the same evolving dark energy signal that DESI sees, that convergence across independent platforms will be extraordinarily compelling. If it does not, if Euclid's data prefer a cosmological constant, then the DESI signal will require a much closer look at possible systematic errors. And there is the Vera C. Rubin Observatory. Located in Chile, it will run the Legacy Survey of Space and Time, ELST, surveying the southern sky over a decade with a camera so large and so sensitive that it will photograph the visible sky every few nights and accumulate a dataset of staggering depth. Rubin and ELST will contribute to dark energy science through multiple channels: weak gravitational lensing, galaxy clustering, and an enormous sample of Type I supernovae, which means it will directly address the supernova calibration uncertainty that is currently one of the main reasons for the spread between 2.8 and 4.2 sigma. More supernovae, better calibrated across a wider range of redshifts, will tighten the constraints and reduce the ambiguity. The picture, then, is this: within the next several years, 3 major independent platforms, full DESI, Euclid from space, and Rubin from Chile, will converge on this question simultaneously. The signal that currently sits at somewhere between evidence and discovery will either be confirmed, refined, or explained away. The answer, in cosmological terms, is close. Not tomorrow, not next year, but on a timescale that people currently alive will see resolved. That is actually remarkable, given the scale of the question. We are not waiting for some technology that doesn't exist yet. The technology exists. It is running. The data are accumulating, night by night, galaxy by galaxy. And when those results come in, when the error bars shrink, when the supernova systematics are better understood, when Euclid's independent view of the same sky is layered on top of DESI's, we will know something genuinely different than what we know now. Either the cosmological constant will have survived one more test and returned to its pedestal, slightly tested but undefeated, or the hints will have become evidence, will have become, possibly, discovery, and cosmology will have to begin the work of understanding what a changing dark energy actually is, what field it corresponds to, how it connects to the rest of physics, what it tells us about the very early universe. Either outcome is extraordinary. The confirmation of a cosmological constant, after all this, would be its own kind of remarkable, a 25-year assumption tested against the most precise map of the cosmos ever constructed and found to hold. The discovery of a varying dark energy would be something else entirely. It would be the biggest shift in fundamental cosmology since 1998. since the accelerating universe was first seen in the light of dying stars. Maybe bigger. For now, right now, in this particular quiet, we are in the middle. Not the beginning and not the end. The measurement exists. The signal is real enough to discuss, strong enough to publish, interesting enough to reshape the questions the whole field is asking, and not yet strong enough to call it. There is something in that position that is worth sitting with for a moment before you drift off, because it is not a frustrating place to be. It only seems frustrating if you think the point of science is to reach answers as quickly as possible. But the point of science is to reach correct answers. And the difference between those two things is where all the rigor lives. The caution the DESI physicists are showing, the consistent, repeated insistence on saying hints, on saying more data needed, on not celebrating at 4 sigma what would require 5, is not timidity. It is precision discipline applied to the most extraordinary class of claims imaginable. It is what separates the field from everything that has ever gotten cosmology wrong in the past. The history of the universe, as we understand it tonight, is the history of a cosmos that began unimaginably dense and hot, expanded and cooled, formed the first hydrogen atoms when it was about 380,000 years old, releasing the light that froze those sound waves into the distribution of galaxies. The waves that DESI is using as its ruler grew for billions of years under the mutual attraction of gravity, and then, roughly 5 billion years ago, crossed a threshold where the dark energy density had diluted sufficiently and the dark energy push had not, and the expansion began to accelerate. That acceleration has been running since, and dark energy, whatever it is, whatever its exact nature, has been its engine. We have been living in an accelerating universe for the last several billion years. The stars in our own sky, the light arriving from the Andromeda galaxy, the faint smear of the Virgo cluster at the edge of binocular vision, all of it sits inside the domain of a cosmos being pushed outward by a force we cannot see and have only ever measured indirectly, by its effects on the light of distant, exploding stars and on the statistical distribution of millions of galaxies across the sky. 68% of everything is dark energy, not dark matter. That is a separate mystery, the missing mass that bends light and holds galaxies together and accounts for about 27% of the total. The ordinary matter, the atoms, the stars, the planets, the people, is roughly 5%. The stuff we are made of, the stuff we can touch and see and measure directly, is the thinnest sliver of the cosmic ledger. The rest is dark, and most of the dark is this force, this push, this thing with an equation of state parameter that might be exactly -1, or might not be. For 25 years, the assumption was, at least we know it's constant. We don't know what it is, but it doesn't change. That one handhold in the dark, that constancy, is what let us calculate the future. It is what made the Big Freeze a confident prediction rather than a guess. And it is that handhold, specifically, that the newest map of the universe has started to make uncertain. Not broken, not gone, uncertain, and there is a particular kind of vertigo that comes from sitting with that honestly, not catastrophizing, not dismissing, just holding it. The largest structure we have ever mapped. 15 million points of ancient light, each one a galaxy that took billions of years to form, each one carrying in its spectrum the record of how fast space was stretching when its light left. All of that data passed through 3 independent lines of evidence and compared against the predictions of a model that has governed cosmology for a generation. And the result? A whisper, a suggestion. a number that is not quite where it should be if the constant is truly constant. The universe has not confirmed this yet. But it has not denied it either. It has done something harder. It has left the question alive. And that is, when you sit quietly with it, one of the more astonishing things a 15-billion-year-old cosmos can do. Keep surprising the creatures it produced. Keep being more complicated than the simplest story about it. Keep offering, even in the deep science, even in the equations, something that functions like suspense, like an unresolved chord, like the feeling of a question that genuinely has not been answered yet. You have the whole shape of it now, the constant that might not be, the map that measured 11 billion years of expansion in a single survey, the forbidden move across the negative one line, the 4 sigma that stopped short of 5, the ending of the universe sitting on a knife's edge between the cold, long silence of the Big Freeze and the reversal and collapse of everything into heat. And the instruments already running, DESI still counting galaxies, Euclid already in orbit since July of 2023, Rubin waiting in the Chilean mountains for its survey to begin, all aimed at exactly this question. All set to send back data that will, within years, tell us whether the hint was real. That is the whole thing, not tidied up, not resolved. Exactly as it is in the field tonight, which is to say, open, honest, and alive. And somewhere under all of it, underneath all the sigma values and redshift surveys and equation of state parameters, there is something simpler. Something that doesn't require the mathematics to feel. The universe is large beyond any number that has meaning to a human mind. It has been running for longer than any timeline we can viscerally grasp. It is mostly dark. And yet we can map it. We can aim a telescope at the sky, connect 5,000 little robotic arms to 5,000 optical fibers, and gather the light of 15 million galaxies all at once, and extract from that light a measurement of how the universe was expanding 8 billion years ago, 7 billion years ago, 5, 3, 1. We can look backward through time by looking outward through space. Because light takes time to travel, and the sky is a record. That is not a small thing. That is one of the more remarkable facts about the situation we find ourselves in. Small, brief, made of the 5% ordinary matter, living on a pale dot in a galaxy among hundreds of billions of galaxies, that we can nonetheless ask the question of how it all ends, and have instruments precise enough to return an interesting answer. Whatever the final verdict turns out to be, that capacity to ask and measure and stay honest when the answer is uncertain, that is its own kind of extraordinary. So if something is keeping you up tonight, if there is some restless corner of your mind turning something over, maybe let it be that. Not the worry of it, the wonder of it. 15 million points of light across 11 billion years, gathered by a machine on a mountain in Arizona, and the story is still going. The question is still open. The universe has not finished telling us what it is. That seems like enough. You know, when I sit on the porch late at night, and I mean really late, when the neighborhood has gone quiet and the only sound is whatever the wind decides to do, I look up at what I can see of the sky, which isn't much from here, just a patch of dark and a few stars through the trees, and I think about how all of it is moving, always moving. Everything we can see and everything we can't. All of it in the grip of something we have only ever measured sideways through the dimness of distant explosions and the clustering of ancient galaxies. And maybe that force is steady, exactly what Einstein put into his equations in 1917 without knowing what he was doing, and it will carry on forever, cold and dark and eternal. Or maybe it is easing. Maybe it has been easing for billions of years, and we are only just now precise enough to notice. Maybe the universe's grip on its own expansion is slowly relaxing. Either way, tonight, it is quiet. The expansion is happening, somewhere beyond anything you could feel. The galaxies are moving. The light is traveling. Somewhere, a telescope with 5,000 robotic eyes is gathering spectra from galaxies whose light left before the Earth existed. And you are here, in whatever warm dark you have settled into, and for now that is the whole world. The big questions will still be there tomorrow. The DESI data will still be there. Euclid will still be in orbit. The Vera C. Rubin Observatory will still be waiting in the mountains of Chile for its turn to look. The universe will still be, as best we can tell, accelerating outward into its own strange future, toward an ending we do not quite yet know. But tonight, you can set it all down. The story got this far. It got to the edge of the known and looked out at the uncertain, and that's a good place to stop for now. You have held it all, the 1998 discovery, the frozen sound wave 490 million light-years across, the 15 million galaxies and their ancient light, the forbidden line at -1, the 4 sigma standing between a hint and a discovery, the rewritten ending, the instruments already pointed at the answer. You have held all of it, and now you can let it go into the dark and just rest. The porch light is on. The night is long and full of stars you cannot see, and galaxies you will never visit, and dark energy you will never touch. And all of it is fine. All of it is just the shape of things. Good night, kiddo. Grandpa'll leave the porch light on.